Hey, y'all. We have two people in the stream. Jasmine, all right. Are you guys here right now? Just pop something in the chat, and I'll see it. All right, so I'm going to get started. So there's a bit of a preface to this exercise. So this stream is about deriving equations from first principles. First principles being like the kinematic equations and F equals ma. And there's a big dislike for physics, right? Because a lot of the people just think it's number crunching, and you're not really learning anything just by crunching numbers into a formula. That's kind of an issue. People don't feel like they're learning anything about nature when they're talking about this kind of stuff. So what Physics 1 has done is made a big emphasis on not numbers. And the way to do that is to build up a lot of the equations that you see from very first principles, because if you know how an equation is derived, you know where the equation comes from, then you really know a lot more about the equation and how it relates to nature conceptually. So this kind of stuff is very important for the AP exam, because knowing how to do this kind of exercise without numbers, just making assumptions about the system, it's very important. It helps you answer a lot of questions, and those conceptual questions, like what happens if this goes up? Does this increase, decrease, or stay the same? You can answer this just with algebra, really. A lot of people try to go through these conceptual questions on like free responses and multiple choice by sort of like thinking about the system, and that's kind of an issue. Because intuition is not going to be good, especially on an AP exam. Your intuition is going to probably fail you. It's failed me multiple times. Math's never failed me. I've failed math. Well, not failed the class, but I've done math badly, and that failed me. But if you do the math right, then you're going to be fine. So a lot of these equations, people often say, why don't you just memorize the equations instead of knowing how to derive them? On a free response, you can't do that. You can't just pull an equation out of thin air on the free response and get full credit. The only equations you can assume are true are the ones that are on the equation sheet. For example, the range equation that we're about to derive and the equation for the max height of a projectile on a level plane, that's not on the equation sheet, so you can't just pull it out of thin air on a free response and do it. However, if you're on a multiple choice and it asks you about it, then don't waste your time deriving on multiple choice, because you can just answer it. No work shown at all. So it's good to have these equations memorized if you can. If you can't, just go through the extra like 30 seconds it takes to derive them very quickly. But on a free response, you'd need to derive it from the equations that are on your equation sheet. So we're going to go ahead and get started. I'm going to describe the physical situation here in this first thing. So what's happening here is we have a projectile fired at angle theta with the horizontal, and it's fired at initial speed v sub 0. And it's going to fly like a parabola, or it's going to trace out the path of a parabola, and it's going to reach some maximum height, and it's also going to land away from its starting point at some range r. And this exercise is to show that you can find both the height and the range by just knowing the speed and the angle. So we have to make some assumptions about the system. So the first equation that's on your equation sheet that you can use, I think this is how it's written. It's it might be x equals x0 plus v0t plus 1 half ax t squared. I think that's how it's written on the equation sheet, but you could write that down and get full credit, or full credit for that part at least. So this is basically saying the position is equal to the initial position plus the initial speed times time plus 1/2 times acceleration in that direction times time squared. So this equation can be applied to both the y dimension and the x direction. So when we're going to work in 2 dimensions here, we're going to start with the x first. So let's subtract x0 on both sides, and we get x minus x0 equals, and this term is 0. there's no acceleration in the x direction because there's no force acting in the x direction. The only force acting is the force of gravity downwards. So there's no acceleration horizontally. And it doesn't matter what t is at that point because that's just 0 times, this acceleration right here is 0. 0 times any number squared is still 0. So that term goes to 0, and then we have this term. So this is kind of a misnomer. This initial speed is in the direction of whatever this variable is. So if we're thinking about the speed in the horizontal direction, we can do right triangle trig. This makes an angle theta, and this is v0. So the first thing is cosine theta. We're trying to find, first off, vx and vy. So cosine theta is adjacent over hypotenuse, which is vx over v0. So vx is equal to v0 cosine theta. And then you have the opposite, or the other trig ratio common one, is vy over v0. So vy, and it's also important that this is the initial vertical speed, is v0 sine theta. So now we have the initial vertical or horizontal speed, so we can plug that in here, and we get v0 cosine theta times t. But what's this quantity right here? This is displacement, right? So if this is the initial position right here, x0, and this is the final position there, x, that distance is just r. So we have r is equal to v0 cosine theta times t. So we need to do a little more work here, obviously, because we don't have a time, right? Time isn't given, so we need to solve for time using the other. I'm gonna put the t here just so it's not confused with the cosine here. So you can just interchange the t and the cosine theta there just by multiplication rules. So the next thing we're gonna do is we're gonna apply that first equation in the vertical direction. So now we get this, and then we get that term just by converting this to vertical direction, and then the acceleration here, I'll write this out actually, plus 1/2, and the acceleration is negative g. It's just a fact to know, t squared. And there's another point here to make. If we subtract this over on this side, y minus y0, the same procedure as last time, and then here we can replace vy with v0 sine t. So we'll put v0 t sine theta minus 1/2 gt squared, just distributing that negative sign. This should be 0, right? It's on a level plane, so that means the final y position is equal to the initial y position. So this is 0. So now we get 0, and I'm going to factor a t out here. T, and then we have v0 sine theta by factoring out a t minus 1/2 gt. So just like an ordinary quadratic, we have two solutions here. There's t equals 0 and v0 sine theta minus 1/2 gt equals 0. So this 0 on the t actually has a physical meaning. So when we're solving for this equation, we're solving for when the vertical displacement is 0. And the vertical displacement is 0 at time equals 0 because it hasn't moved at all. And it's also 0 at the end of the trajectory. So we're not really worried about this solution, but it's there. So we're going to solve for t in this case because we need to solve for t to get here, because we do know this v0, we do know this theta, and we know g. So we have an equation of one unknown only, and we need to substitute that unknown into this equation. So now we have v0 sine theta equals 1/2 gt, just adding 1/2 gt on both sides. And now we get t is equal to 2v0 sine theta over G. We can substitute this back into here and get V0, and T is 2V0. Yeah, 2V0 sine theta over G times cosine theta. And I'm going to rearrange in terms here. This is V0 squared times 2 sine theta cosine theta over G. If you're in pre-cal, or if you've taken pre-cal, because I don't think normal pre-cal classes will get there yet, or are there yet. This right here, 2 sine theta cosine theta, this is also equal to 2 sine theta. Rather than here. Not 2 sine theta, sine of 2 theta. Sine 2 theta. So we can plug that into here, and then we get the final expression for the range as V0 squared sine of 2 theta over G. And that's the expression for the range. And the height is a little easier. I'm going to expand the canvas a little bit so we can do more work. Expand the width. We'll do 1200. There we go. So we have this expression for the range. I'm going to do the height in a different color. So there's a key point that we need to look at here, and it's a simple derivation, I think. We're going to use the kinematic equation. This might be how it's written on the equation sheet. V0 squared plus 2AD. Maybe that's how it's written. It might be written delta x, actually. That would make more sense, to be honest. So we're going to apply this to vertical direction. So we get Vy squared is equal to, and we know what this in the vertical direction is. This would be V0 sine theta squared. And the acceleration is going to be negative g again in the vertical direction. And the vertical displacement at the max height is just going to be that h that we're looking for. However, at the top of the path, the maximum or the vertical speed is 0. It has to come at rest at least vertically for it to be maximum height. So now we have V0 squared. And this might be new notation, sine squared theta. This just means sine theta squared. So sine squared theta is just sine theta squared. I really hope you can't hear the bassiness. Someone's blasting music. That's annoying. It's literally a Tuesday night. People are blasting music. All right. So we have this equaling 0, which means this is equal to 2gh. Therefore, the max height is V0 squared sine squared theta all over 2g. And that's that equation. And looking back at it, no, I put the square there. That's right. Okay. So as you can see, these are both the height and the range are proportional to the square of the speed. That should make sense. The faster you shoot the projectile, the longer it should go, the higher height it should reach. However, they're both differing by a certain angle. And it should make sense. So when we're looking at the range is only a function of theta, right? If we're looking at only theta. And sine of any angle, the maximum value, that can be as 1. If you don't believe me, you can graph that on Desmos or something like that. So the max range occurs when theta is 45 degrees, because sine is 1 when the inside of sine is 90 degrees. And the height here, if we're looking at the height here, we have this only being function of theta as well. However, it's a different kind of function. The height is maximum when theta is 90 degrees, which means the max height that it reaches is maximum if you shoot it straight up, which should make intuitive sense. So those are two equations. Again, you're going to have to derive those in a free response question. You were asked about it, but on multiple choice, just know the equations. So the next one we're going to be doing is the classic blocks on an incline, and we're going to be solving for both the friction force and the acceleration of the block. So we're going to start just like any other dynamics problem. We draw a free body diagram. So the force of gravity pointing downwards, mg, the normal force perpendicular to the plane, and then we have a friction force opposing motion. This is assuming the block is moving down the plane. So we need to split this up into its components. This angle is theta. This is mg cosine theta. This is mg sine theta. So now we do F equals ma in both directions. We have the sum. That's a bad sigma. That's a great sigma. Wow. We have the sum of the forces in the x direction, or we're going to do parallel direction. Our coordinate axes is set up like this. This is the parallel direction, and this is the perpendicular direction. So we have the sum of the forces in the parallel direction is equal to ma in the parallel direction. But the first thing we need to do is solve for actually the, let's see if I can replicate that perfect sigma again. No, I can't. F's in the parallel direction, which is n minus mg cosine theta. And it's not accelerating in the perpendicular direction, so that means that this is 0. Because if it were accelerating, that means it would be leaving the plane like jumping up, which we can assume it's not doing. So now we have the normal force is equal to mg cosine theta. And from there, we can solve for the friction force, right? You should remember that the friction force is, or the kinetic friction force is mu k times n. This is the coefficient of kinetic friction times the normal force. So we have the friction force is mu k mg cosine theta. And that's the first formula that we're deriving. So now we need to do stuff in the parallel direction. There's only one force acting in the parallel direction, and that is a friction force. We're going to assume this way down the plane is positive, which means the friction force is acting in a negative direction. So we have ma parallel is equal to negative the force of friction. And we already have that equation here, which is negative mu k mg cosine theta. Well, no, that is incorrect. We have another force pointing down the plane positively, which is the component of gravity pointing down the plane. So now we have mg sine theta minus mu k mg cosine theta. So that's just the friction force. And there's masses on both sides, so we can divide both sides by mass. And now we get the acceleration in the parallel direction is, I'm going to factor out a g here. G sine theta minus mu sub k cosine theta. And the magnitude of acceleration is just going to be the square root of acceleration in the parallel direction squared plus the acceleration in the perpendicular direction squared. But this is 0. This right here is 0. So this becomes square root of this squared. And this is just a parallel, which is just g sine theta minus mu k cosine theta. Running out of room here. So now we have this formula as well. So we solve for both the acceleration and the friction force. And here a big takeaway is that the mass or the acceleration is independent of the mass. And this is a great case here. Question could ask, like, what happens to the friction force or the magnitude of the friction force if the mass of the block is increased? And it's kind of hard to tell from intuition. In my opinion, as an introductory student, it's kind of hard to tell from intuition that the friction would increase. However, if you see this equation right here, it's very clear that it would increase if mass increased. And for the same case here, if it asks what happens to the acceleration of the block, the magnitude of the acceleration of the block, if the mass increase. And it's kind of, you can make a case for both situations, right? You could say, well, if there's more mass on the block, then it's, or if the block has more mass, then it's harder to accelerate, so the acceleration is lesser. Or if the mass is increased and the block has more weight, which means that it will travel faster down the incline. But the real case that the math proves here, which is objective, right? The intuition you have is subjective, and subjectivity is not really very welcomed in the sciences that much because it often leads to wrong answers, just like believing that it changes if mass increases, believing the acceleration changes. And you can see here that on this bottom right equation that the acceleration down the incline is not dependent on mass at all. So that's an example of it. So we're going to be doing another problem that I think is a lot more revealing and probably something you didn't do. So you have the situation here, the physical situation here is you have a plane and you keep on increasing the angle. And you're trying to find at which angle. This isn't good. We're gonna do. We don't know this, and we do know u sub s. So you're trying to find at which angle the block slips or not. The maximum angle that the block won't slip. So this is again a free body diagram. It's the same free body diagram as last time. Normal force, weight, friction, mg cosine theta, and then mg sine theta. So now we have, in the same case as before, the normal force is mg cosine theta. So the acceleration down the incline is mg sine theta, or g sine theta. That should be in parentheses. It's the same acceleration term as last time, except this time it's it is with a static coefficient instead of a kinetic one. Except there's a big difference in what we're looking at here. There's no acceleration, right? If there's an acceleration, then it's moving, and if it's moving, then the friction is kinetic. But in this case, it's static, so there's no acceleration, so this equals 0. And the only time this could be true is if this term equals 0, right? Because g is never 0, so the only solution that we can actually extract from this is sine theta minus mu s cosine theta equals 0. And now we have an expression in terms of only mu and theta. But how would we solve for theta? So we're going to subtract or add mu s cosine theta on both sides. So we have sine theta is equal to static coefficient of friction times cosine theta. And we're going to divide cosine theta on both sides and get mu s equals sine theta over cosine theta. So how do we isolate theta from that, right? Like there's two functions. You can't really just take the inverse on both sides. So we're going to do some cool geometry that you may not have seen before. So we have some angle theta and some hypotenuse r. We know that, or we know this distance right here. Solving for this distance, we're going to use sine theta equals, we'll call it y, opposite over hypotenuse. So this is our sine theta, and this is our cosine theta. But now we're going to look at the tangent of the angle. So tangent is opposite over adjacent, right? So we have tangent of theta is opposite, which is r sine theta over r cosine theta. And the r's cancel, and we get this cool identity. The tangent of some angle is just the sine of that angle over the cosine of that angle. That may be a familiar formula if you've taken pre-cal again, but if you haven't, then now you know it. So now we know that this is the tangent of theta. So applying arctangent on both sides, we get theta is the arctangent of the coefficient of friction, or the static coefficient of friction. And this is theta max, rather. This is the maximum angle you can swing it out to so that the box never leaves the incline or never starts traveling on the incline. And we're going to do an example here. We're going to plug in a number here just to see how it looks. So we're going to evaluate this for mu sub s, we'll say is 0.3. That's a reasonable number. So I'm going to do this on my phone. So this means that the maximum theta this can make is equal to the arctangent, or the inverse tangent, whatever you want to call it, of 0.3. And this is about, let's see, arctangent of 0.3, 0.291 radians. So that's times 180 divided by pi. That's about 16.67 degrees. And that should make sense, right? That's a pretty small static coefficient of static friction. So you should be able to, the angle shouldn't be that large. However, if you have something like what this means is that if you have an infinite static coefficient of friction, you could swing it all the way up 90 degrees, because the arctangent of infinity is 90 degrees. You'll learn that in either pre-cal or cal, depending on how deep your pre-cal teacher goes. So yeah, that means that the only way to get something to stay completely vertical is to have an infinite coefficient of friction, which I hope you know doesn't exist, because that would imply an infinitely rough surface, which doesn't really make sense. So that's that. Again, I don't think this would be fair game on a free response, just because you'd have to know that trig identity to completely work with it. But now you know how to write it. And if it asks, like, it might ask, like, what happens to the maximum coefficient of static friction if theta increases, or the other way around, what happens to the maximum theta if this increases. And if you know the shape of the arctangent graph, which looks something like this, and it levels off at around 1.57. This is y, this is x, this is y is equal to arctan x. We'll keep the notation consistent. From this graph, you can very clearly see that in this equation right here that we have, if the static coefficient of friction increases, and the maximum angle you can swing out the plane also increases. And that is a little more intuitive than the previous examples we've given with the whole acceleration on the incline, or the range equation. It's very not intuitive at all. I'd be very impressed if you could pull that out of thin air without deriving it or remembering it. So yeah, that's that example. This means that you could find the static coefficient of friction pretty easily for between any two surfaces. You just find a surface, take a video of you take a video of you just swinging the material up that the block is on, and taking a slow-mo video and finding at exactly what angle the thing starts sliding. And you could just find the angle by using a camera. Like if you have a phone, you can just simply look at the picture, measure it with a protractor, the angle, because the angle is going to be the same regardless of the scaling of the photo. And then you could find the maximum theta, and then you could take the tangent of that theta and find the coefficient of static friction between the block and the plane. And I honestly think that's the easiest experiment you could do to find something like that. Now, there's other ways you can do it. You can set up like a pulley system to find it, but that's kind of too much work in my opinion. I think that's kind of unnecessary. So the next one we're going to be deriving is we have two blocks, one of mass 1, one of mass 2 on a pulley. The pulley is massless. There's no friction in the pulley, which means the tension of the two strings are equal, which is very important. And we're going to be solving for the acceleration of the system. And the acceleration of the system is probably kind of a vague term for most students. So what this means is, well, the first assumption that we can make here is the string stays taut, right? Where's something I could keep taut? This charger right here. This is obviously the loose string right here if I'm just doing this, but the string stays taut if I pull on it on both sides. That's what that means. The tension, there's actually a force of tension because the string is taut. It's being pulled, stretched. Not as stretched as more springy. It's not springy. Well, it might be on a molecular level, but that's beside the point. So the acceleration of the system here just means the acceleration of either mass 1 or mass 2. The accelerations are going to be the same. If the accelerations are different, if I take this charger again and I accelerate both my hands, but one slower than the other, the string starts to become not taut. And if I accelerate this hand faster than this hand, the string snaps. So that's the case here. The acceleration system just means you can either think of the acceleration of mass 1 or mass 2. They're both going to be the same. So the first thing we have to do is draw a free body diagram. Actually, no, not even the first thing we have to do. We have to establish what the positive direction is. So, for example, on this inclined plane problem, we established a normal 2 axes perpendicular to each other coordinate system here. But the great thing about a physics problem is that you can set your coordinate system to whatever you want. It's going to work as long as you set it up right. So we're going to choose the coordinate system that makes the most, gives us the most ease. And the coordinate system we're going to set up is these two strings being in the same coordinate system, being as if they were stretched out on the same line. So that means we're going to designate this to be the positive direction. Like I said, for the same reason, you can set it up any way you want whatsoever. As long as you get it right, your answer will be right. However, for example, if you tried to use this curvy coordinate system on this problem, you're likely going to end up with something that's not solvable on paper. You have to use a computer, but you would get the same acceleration. So we have this now, and we're going to draw the free body diagram for M1. So for M1, there's a force of gravity pointing downwards, and there's a tension force pointing upwards. And for the second one, we have the same case. However, we have to really think about what's positive and what's negative. So for the M1, we have down being positive. So the force of gravity is going to be positive. So when we're summing the forces, I need to get better drawing sigmas. When we're summing the forces in the vertical direction, we need to take account for the negative sign. So this would be plus M1G, and we are summing, so it's adding. However, the tension is negative. So we now have M1G minus T is equal to M1A. And that's really all we can do with that equation, honestly. We're going to do the same thing. We're going to label this mass 1. And for mass 2, in the same case, we have to be careful with what's positive and what's negative. This is going to be tension is now positive direction, right? Because on M2, from this diagram we drew, the tension is now pointing in the positive direction. So now we have T minus M2G is equal to M2A. Quick side note here, you could do the coordinate system the other way. You can make the other direction positive and it'll get the same answer. You'll just get a negative acceleration, or the acceleration will be the negative of the answer we are about to get. That's fine. As long as you clearly define what's positive and what's negative, they're really the same physical answer, right? Like if you think of like me dropping a ball on the ground and one person says, oh, the acceleration is negative g, and one person says the acceleration is positive g. Well, they both mean the same direction. They're just mathematically describing the system differently. And the math isn't the physics. The physics is how nature is. And the mathematical models are what physics uses to describe nature. So we're going to solve for tension here. We get tension is equal to M2A plus M2G. But these tensions are the same. It's not something that I can explain right now. You're going to have to wait until rotational dynamics. And I'm pretty sure even a problem like that is very physics C-like, not very physics 1-like, because the math is very heavy. The algebra is very heavy. And you end up putting too much emphasis on the math for College Board to like it for physics 1, because they try to put a conceptual emphasis for physics 1. The reason for that is because physics 1 in college is algebra-based physics, and algebra-based physics is what the pre-med students and the biology students and the biochemistry, well, not necessarily the biochemistry students, but mostly the biology and the pre-med students take. And they need to have a more conceptual understanding for the MCAT, which is basically the admissions test for med school, whereas the calculus-based ones, physics C, or the physics C equivalent, are very math-heavy because they're what the engineers and the physicists and the chemists take. So they're going to have to, know the numbers very well, whereas the biology and the pre-med students aren't going to have to know the numbers very well. A little bit of a sidetrack. But so now we can substitute this tension into this tension because they're the same thing. So now we have M1G minus tension minus M2A plus M2G is equal to M1A. Distribute the negative sign. We now get M1G minus M2A minus M2G equals M1A. We know we want the acceleration to be isolated, so we are going to subtract this M2A term on both sides. We get M1G minus M2G is equal to M1A. So adding to both sides would be plus M2A. We're going to factor a G out to make the algebra more simple. We're going to do it this way. M1 minus M2G is equal to, factoring out the A here, M1 plus M2A. And now we divide on both sides. And we get M1 minus M2 over M1 plus M2 multiplied by G is equal to the acceleration of the system. And we're going to extract some physical information from this equation that we just derived. So let's see. So we're going to find out the case in which it accelerates in the positive direction that we designated, if the string or the pulley system accelerates in the way of mass 1. So for it to accelerate that way, acceleration has to be positive, right? So if we're looking at in the case where the acceleration is positive, this means that this whole thing is positive. Well, G is always positive, and M1 plus M2 is always positive because M1 and M2 are both individually positive, so their sum is positive. So the only case that could be negative is this case right here, we use some mathematical notation. This double arrow means two mathematical statements are equivalent. M1 minus M2 is greater than 0, which means it'll accelerate that way if M1 is greater than M2, which makes sense because if M1 is greater than M2, the strings are going to be pulling more on that side, which means that the system will accelerate in the other direction. And for the opposite case, A is less than 0 is equivalent mathematically to M2 being greater than M1, which is nice, I think. It's a nice little equation. Again, it's worth memorizing. If not, just go through the time to derive it. It takes a lot less time to derive by yourself when you don't have to explain the process to the people watching every time you do it. But that's really an important equation to know. You might be able to set up an experiment to solve for the acceleration due to gravity. You can solve for the acceleration of the system by estimating it with kinematic equations. The acceleration will be constant, so you can use kinematic equations you can record the system, you can release it. If you know both the masses, you can release it and record it and jot down some times. You can jot down the displacement as a function of time. Because if you have, let's look at the displacement of this one, considering the positive direction again. You have the displacement, why am I using x? It's definitely vertical. Delta y, if you're starting the system at rest, there's no initial speed, so it should be 1/2 gt squared. Again, you could also use that equation to solve for the acceleration due to gravity. You can do a lot of things to solve for the acceleration due to gravity in this case. I think a really good thing here is if the masses are equal. If the masses are equal in this ratio, then this is equal to 0. Right? If the masses are equal, M1 minus M2 is 0, so the acceleration of the system is 0. So, for example, if you had a problem where you had two things hanging out of pulley and it said, well, what if the mass on both of them was increased? What if variable m was increased? What happens to acceleration? Does it start accelerating? If you're given like a diagram like this, where one string is significantly further down, and they both have mass m, and it says what happens if you increase variable m. If you increase both the masses, will accelerate downward. Will accelerate in the way of the longer string. And the physical intuition you should have is that it will, because the string is longer. That just makes sense to me, but it's wrong according to this equation that we just came up with. So this is a great case in which the intuition fails and math succeeds. And that's really important to be able to do this algebra without being given equations or without being given known variables to do. You have to assume known variables, the really easily measurable variables like mass, time, spring constant, displacement, all those good, very easily measured variables that you can measure in a lab setting. And you should have a good intuition of what kind of variable is easy to measure, just based off either lab experience or just general experience, right? It's hard to measure a force per se. It's much harder to measure a force than measure a distance because you need a special apparatus to measure a force. It's much harder to measure a speed than to measure a distance because you need a photogate to measure a speed, but you only need a ruler to measure distance. It's much easier to measure mass than something else just because oftentimes the masses aren't given, or you can do a spring experiment, a spring-based experiment where you can solve for the mass. You can do a lot of things. So the next thing is a little more complicated. We're going to be driving Kepler's third law. And Kepler's third law says that the square of the period is directly proportional to the cube of the distance between two planets. And that's how you solve for how long it takes for, or really it's an even better way to solve for distance, how far away a planet is from ours. Because it's much easier to indirectly measure time than indirectly measure distance, right? If you think about it, if you think of like a car crash happening far away from you, or any sort of event, really, I don't know why car crash came to mind. I might just be in a destructive mood right now. But it's much easier to measure the time it takes for something to happen, or how long ago something happened, than how far away something happened without a special apparatus. So time is even easier, one of those even easier more easily measured variables, if that makes sense. So you can use that to solve for how long or how far away something is. So the first thing we need to start off with here is centripetal force. And this says the sum of the forces acting centripetally on a system is equal to the mass of whatever body it's acting on times the speed of it squared. Why did I put an alpha there? Divided by the radius of curvature. This basically says there can be a net force on something, or there could be a non-constant acceleration with a constant speed, because that means the acceleration, or there could be a non-zero acceleration for a constant speed, which is a very important detail and especially a great lesson with vectors. So there's only, when we're thinking about the interaction, this is the sun right here, and this is the planet. I purposely omitted the mass of the planet because it's going to end up not mattering. So the way we do this is we draw a free body diagram. We'll draw the sun as a dot. This is a dot, distance r based off the diagram we have here, and there's a force acting inwards, which is big G, big M, little m over r squared. That's Newton's law of gravitational motion, or Newton's universal law of gravitation. Not sure the official name for it. I think that might be it. That's pretty much that equation. If you don't know it, you will learn it. So we're assigning m here, even though we don't know m, but it'll end up not mattering, just to make the problem more clear, or the work more clear. So we're solving for how long it takes for it to rotate in one full revolution. So now we have, there's only one centripetal force. There's only one force acting inwards, and that's the gravitational force. So now we have G big M little m over r squared is equal to mv squared over r. And you should already notice that one mass, the mass already goes away. It already doesn't matter that early in the step. So now we have G M. We're going to cross multiply the r this way and the r squared this way. GMR equals v squared r squared. So we're going to factor out that square. There's a reason we're not canceling so far. It's equal to v times r squared. Actually, no, we'll go ahead and cancel an r there. So now one r cancels on both sides, and now we have gm is equal to v squared times r, or v squared is equal to gm over r. And it might be a little obvious how to, or it might not be a little obvious how to solve for the period here. So we know that speed, the magnitude of velocity, is equal to distance per time. Let's say distance per time. So how long does it travel? How much distance does it travel for something to travel full revolution? That's just the circumference of the circle here, the circumference of the rotation, and that is just 2 pi r. You should remember that from geometry. 2 pi times the radius over however long it takes for it to solve, or I'm tired. However long it takes to do that full revolution. So now we have v squared is equal to 4 pi squared r squared over t squared. And we can substitute that in for the v squared here. We get 4 pi squared r squared over t squared, just by substituting the v squared in, is equal to gm over r. We're going to cross multiply again, cross multiply like that. 4 pi squared r cubed is equal to big G, big M, big T squared. And now we have 4 pi squared, dividing both sides by gm. Gm r cubed is equal to t squared. And we have successfully proven that the period only depends on the radius and the mass of the planet. Nothing else, which is really cool. Or not the mass of the planet, mass of the sun. You'd think that the orbital period, however long it takes to complete a full cycle, would depend on the mass of the planet. but it doesn't. And this thing can be applied to other things like a satellite around Earth. And it's really cool that kind of thing happens. So because we have time, I'm going to do a little extra bonus question. So the assumption we made here, when we're looking at this interaction here, there's also an equal and opposite force here, Newton's second law. So they both pull each other. So why can't we make the assumption that the second mass stays stationary, that it moves in a perfect circle? And the reason why is because the mass of the second one is so bigger, and we know from F equals ma, even if it's increasing or exerting an equal force, if the mass increases, then the acceleration decreases. Right? If we're dividing mass on both sides, we get A is equal to F over m. So for the force to stay constant, the force is a constant. Or if the mass increases, the acceleration decreases, just based off of that proportionality relation there. So we're going to do something a little unorthodox because I have the time to do it, and I think this example is really cool. So what if we had two planets of equal mass? What would their orbit be? What would their period be? This is called a binary star system. So they both exert the same force on each other. So this is mass m, this is mass m. We're going to assume equal mass. We know that the force is gmm over r squared. However, the masses are equal. So this is now gm squared over r squared. But there's a distinction you have to make here, because this r is not the radius of curvature. This r is its total distance. The radius of curvature is half of r. We have to split this down the middle and think of the radius of curvature, which would be r over 2. So when we have to really be careful about the equations we're using. So now we have gm squared over r squared. This is the centripetal force is equal to mv squared. However, it's not over r, it's over r over 2. Because this r right here in Fc equals mv squared over r, this r right here is the radius of curvature, which is different than the total distance between them. So now we can cross multiply r over 2 gm squared is equal to mv squared r squared. And we're going to notice something cool. Now the system actually does depend on the mass, the individual masses. So 1m cancels, 1r cancels. Now we get gm over 2 is equal to v squared r. Same substitution for v squared here that we made. But now it's not this r anymore, right? When we're thinking v is equal to the circumference over the period, as before, the circumference is now r over 2, or 2 pi r, 2 pi times the radius of the circle, which is r over 2. So r is the distance between the two planets divided by time, and these cancel, so we get pi r over t. So now we substitute that in, gm, we're going to multiply the 2 over. 2 times pi squared, just squaring for v, r squared over t squared, times r, multiply t squared over, we get t squared, big G little m is equal to pi squared r cubed, and we get now t squared is equal to pi squared over big G, big M, or little m actually, r cubed. So we get two different equations. One is off by a factor of 4. If the planets are of equal mass, there's an even more enriching case of where the masses aren't equal, but that's kind of outside the scope of physics 1. You have to find the center of mass of the system, and that's what it would rotate around. So yeah, I mean, it's kind of interesting that the equations are different, even though the system is kind of the same. You just make a different assumption about the system. So if you wanted to, let's say, if you had data and you wanted to solve for the mass of the planet in a lab exercise or AP free response. You have t squared on this, or rather you have r cubed on this axis, t squared, and you have the data for multiple planets, how long a year is on each planet, and how far away the planet is from the sun. You have a slope here with a line, and this slope is 4 pi squared. GM is equal to the slope. So you have multiplying both sides by GM. 4 pi squared is equal to GM times the slope. And now you have, solving for big M, you have M is equal to the denominator first. We have 4 pi squared. Actually, no, the 4 pi squared is on the top. We have G, big G times the slope. There we go. 4 pi squared. The same case here, we have the mass of the planet is equal to pi squared, doing the same exercise over G times the slope. So there's something enriching here, right? When we look at, like, if we see a binary star system somewhere in the galaxy, it's very clear to see, or somewhere in a faraway galaxy, somewhere in our galaxy, you can very easily observe the period, right? It's just how long it takes for the masses to change. It's very easy to observe that. So you can very easily calculate the mass just by doing the same exercise, by not even by taking the slope, just solving for the mass, right? You could just measure the radius with some computational techniques, or if there's some nearby galaxy that you can measure with a frame of reference with, you know the distance and you know the period, and G is just a constant. Big G is just a constant. I don't have the numerical value memorized. Pi squared is also a constant. You can solve for the mass. So if you want a challenge problem, I would recommend doing this on your own, solving for the case where they're not the same, and solving for the period. In that case, one distinction here is that planets don't orbit in circles. Planets orbit in elliptic orbits, meaning the circle's kind of squished and fatten out. So kind of like a potato shape like that. And the reality is that, like, the equation still holds. I could not tell you why. I've literally tried solving for the case where solving for it using autocalculus, and I just can't figure out why the equation still works for this. It's one of these distances, I'm pretty sure, that that is considered R. I'm not sure which one. I think it might be this one, just based off of my loose memory. But yeah, that's Kepler's third law. You might not have learned it yet, but now you know how to derive it just with simple circular motion, which is nice. So we're going to recap the stream a little bit, just because we have the time to do that. So the first thing we derived, or the first two equations we derived, are the equations for range and height. And we saw that range and height both only depended on the initial speed the projectile was shot at and the angle it was shot at. And we could tell with these equations that the maximum range occurs when theta is 45 degrees, when it's shot at a 45-degree angle, but the maximum height occurs when the projectile is shot straight up at a 90-degree angle. The second one's a little more intuitive than the first one, but if you think about it, the first one should be also intuitive. And the second one, you don't really need intuition, or you don't need the math to know that, but the first one, you probably definitely do need the math to know that for certain. The next one, we derived the equation for the acceleration of a plane down an incline facing friction with angle theta and coefficient of friction UK. This is kinetic friction. We also solved for the force of friction, which we found out was just mu mg cosine theta, which is an equation you should probably, again, memorize, but on free response, you can't just jot it down and pull it out of thin air. You have to show where it came from. The third one, we solved for the expression for the maximum angle that you can make between a block and a surface, and there's a coefficient of static friction, mu sub s, between them. And we found that it was only the arctangent of that coefficient of friction, which I'd be surprised if you could just come up with that out of thin air. we said that it's probably not fair game for an AP response because you have to know that trig identity, the tangent theta is sine theta over cosine theta. But it's still good to know, regardless if you're asked about it. We derived the equation for the acceleration of a block and pulley system, a 2-block pulley system, and showed intuitively that if mass 1 is greater than mass 2, it'll accelerate towards the string with mass 1, and the opposite case, it'll accelerate the other way if mass 2 is greater than mass 1. And for this one, we solved for, we proved Kepler's third law using centripetal force equations, and proving the square of the period is proportional to the cube of the radius of curvature. And we also did a cool little exercise with binary stars. So that's the stream. 3 people around here. I hope you guys enjoyed the stream. As always, I'm going to put my my Instagram here. If you need help with really almost any STEM homework, I can help with at jjeffries12. You can follow it. You can DM it if you have a question. I'll respond to it as soon as I see it or as soon as I possibly can. You can ask me chem, physics, math, stats, some biology questions I can answer. If they're very chemistry heavy biology questions, I can probably answer them. So yeah, that's the end of the stream. Hope everyone learned something. Have a good night.